So this lesson is going to be about angles on the coordinate plane and radian measure, which is a different way of measuring angles. I want to start with the basic concept of what an angle looks like on a coordinate plane. So here you have a basic coordinate plane drawn, but instead of labeling our axes with x and y, we're labeling what we normally think of as the positive x-axis with a 0 degrees. So angles when drawn on the coordinate plane will start with their initial side facing 0 degrees, which is the positive, like, x-axis. And then if you wanted to create, for example, a 42-degree angle, you would rotate that arrow up 42 degrees. So we're going in the counterclockwise direction when we create a positive angle on the coordinate plane. So not the same direction as the hands of a clock. So you can see why this would be about a 42-degree angle. It's an acute angle. If I were to then raise this all the way up straight, I would have created a 90-degree angle. So that's why up at the top of where we usually have the y-axis, we label it 90 degrees. We can imagine continuing to rotate this red arrow around. 180 degrees would be the negative direction on the x-axis. 270 degrees would be the negative direction on the y-axis. And if you went all the way around and back to where you started, you would have gone 360 degrees. And then you could even keep going. You can create angles that are greater than 360 degrees. For example, a 400-degree angle. It would mean that you've gone all the way around. So starting from the initial side of 0, gone all the way around the circle 360, and then 40 more degrees. So that would put you back here in the first quadrant again. So you can think about angles on the coordinate plane as basically just spinning this angle around and around and around, and stopping when you've gone the number of degrees that you're trying to draw in the counterclockwise direction. Some definitions that you're going to want to know. So here we have a red angle drawn. This one is called the initial side. I used that word before, but now we should write it down and define it. Right, it's the initial side of the angle that is pointing at 0. And then where the angle ends is called the terminal side. So initial meaning the start and terminal meaning the end. What we can't tell from this picture is how many times did we spin around before we ended up at that terminal side. So this to me looks like approximately a 120-degree angle. If we started from 0 and rotated into the second quadrant, we created a 120-degree angle. But just from what we had shown, we have no way of knowing that we didn't actually do this. Go all the way around the circle first and end up back there, which would be a 480-degree angle. How did I get 480? I basically just did 120 plus 360. So as if I just spun all the way around the circle and then did that 120. But we could have even changed to green. We could have even started at 0, gone all the way around the circle, all the way around the circle again, and ended up there. So we have no way of knowing that unless we draw that spiral, that directional arrow to show where I started and how many times I spun around to get there. So though it's not conventional, you don't need to draw these little spirals that I keep drawing. Sometimes it is nice to show them. And when you do this on your homework, I'm going to want you to show it so that I know you know how many times you went around the circle before you ended up at your terminal side. So if I ask you to draw me a 480-degree angle, it's going to look like this, but I'm going to want to see that spiral so I know you went all the way around the circle. The other things we should define on this slide are quadrants. We name them with Roman numerals, but we read them as just 1, 2, 3, 4. So that first quadrant 1 is the positive quadrant on the coordinate plane. And then again, going in a counterclockwise direction, quadrant 2, quadrant 3, and quadrant 4. So I might ask you, the terminal side of a 120-degree angle lies in quadrant blank, and you have to figure out, okay, 120 degrees, that's going to end up being in quadrant 2. Or 240-degree angle, where is that going to end up? And you think about it, it's going to end up in quadrant 3. So one thing you'd be asked to do is draw an angle with a given measurement in standard position on the coordinate plane. So standard position is when the initial side is pointing at 0, and that's how we're going to do all of the angles for this class. To draw an angle at 240 degrees, we just need to remember this is 0 and this is 90, this is 180 and this is 270. So as I spin this initial side around to create my terminal side, we go 90, we go 180, we have to pass the 180 but not quite get to the 270 in order to create a 240-degree angle. So it doesn't need to be precise, but it does need to end up in the right quadrant and roughly in the right place in that quadrant. And I want you to show me, like I said, a directional arrow so I know where you started and how many times you spun around to get to that angle. So there's a 240-degree angle. 500 degrees, I want to see your initial side at 0. Think about spinning around 500. So if I go all the way around the circle, that's 360. In order to get from 360 to 500, I need to go another 140. So if this is 0, 90, 180, 140 is going to end up being somewhere in the second quadrant, about here. But the directional arrow will show that we actually went all the way around the circle before we got there. So there's a 500-degree angle. And then a negative angle, I didn't mention this on the previous examples, but if you go in the other direction, so clockwise when you leave your initial side, you can actually create a negative angle. So if I'm going to go 50 degrees in the negative direction, I think about that negative as a direction. It tells me to go clockwise instead of counterclockwise. You think about this as being 0, and this as being negative 90 degrees, right, if you spin the other direction. So 50 degrees is going to be somewhere approximately here. And the directional arrow this time will point down, so I know that you went starting from the initial side, you started going clockwise to create this negative 50-degree angle. Now, a negative 50-degree angle, just so you're thinking about it correctly, is the same, or is going to look the same, as a positive angle that went starting from 0 all the way around to get to the same place. So in this case, a negative 50-degree angle is the same as a positive 310-degree angle, because it would end up in the same place. The terminal side would be in the same place. When you have two angles that the terminal side is actually identical, ends up in the same place, we call those coterminal angles. So coterminal angles are angles whose terminal sides overlap or coincide. So when I think about going a full 360 degrees, either counterclockwise or clockwise, to end up back where you started. So if you have, let's say, a 45-degree angle right in the middle of quadrant 1, right? A 45-degree angle is going to be coterminal with, if you just continued rotating, went all the way around another full 360 from there, you would have gone 45 plus 360. So 45 degrees is coterminal with the angle 45 plus 360, which is 405 degrees. Right? And I could even spin again. I could go another 360 degrees. That would be coterminal with 405 plus another 360, which would be 765 degrees. It's a big angle. But I could keep going like this forever to find more and more coterminal angles that will look the same. The only thing that will be different is how many times they spun around to get there. And I can go in the negative direction. Instead of adding 360, I can subtract 360, spin the other way, right, go in the negative direction, and figure out, well, this is also the same as a negative 300 and, let's do this math, right, 15-degree angle. Or I could subtract 360 again. That would be the same as a negative 675-degree angle. So you can find coterminal angles simply by adding 360 and continuing to add 360, or subtracting 360 and continuing to subtract 360. So one thing you'll be asked to do in homework is find one positive angle and one negative angle that are coterminal with, for example, negative 45. So a negative 45-degree angle. To find something that's positive and coterminal with that, we'll add 360 until we get a positive angle. And the first time you add 360, we're already at 315. So there's a positive coterminal angle. To find a negative one, I'll subtract 360. And that's going to give me negative 405. So I found one positive and one negative coterminal angle with negative 45. With B, that's a 395-degree angle. If I add 360, in fact, you know what I can do, because I recognize that this number is already bigger than 360. If I subtract 360 once, I'm still going to be positive. You could also add, so everyone's answer may be a little different to this question, but 35 degrees is an example of one positive coterminal angle with 395. If I wanted to get a negative one, I'm going to take that 35 where I landed, subtract another 360. This I know will bring me into negative territory, and so I'll be at negative 325. So there's a positive and a negative coterminal angle with 395. And now we jump into talking about radian measure. So this is a different way of measuring an angle that's not based on degrees. And this is a very new concept at first, but it's not complicated once you start getting the hang of it. So as we know, a circle is 360 degrees. If you were going all the way around the circle, you'd travel 360 degrees. A radian, instead of a degree, is based on the circumference of the circle rather than the degrees of the circle. And more specifically, it's based on the circumference of what's called a unit circle. A unit circle is a circle that has a radius of 1 unit, so 1. So I'm picturing on this circle on my coordinate plane that the radius of the circle is 1, which means I know that the circumference is going to be the diameter times pi, so the diameter of the circle would be 2, times pi. So what I have here is a circle with circumference 2 pi. Instead of talking about splitting my circle into 0, 90, 180, and 270 degrees, I'm thinking about my whole circle's circumference as being 2 pi, and imagining splitting it into different arc lengths. So rather than degrees, we're thinking about different arcs. This can be a little, like I said, new at first, but we're still starting with 0 here. So instead of labeling it with 0, 90, actually maybe I will, just to put us back in the context of what we already know. 0, 90, 180, and 270, and then of course 360, would be the degree measurements if we spun around this circle. When you're talking radians instead, let's put degrees on all these so we're accurate with our units. When you're talking radians instead, we're still starting at 0 radians. But when we've gone all the way around our unit circle, we've traveled 2 pi radians. So as I said, it's based on the circumference of this unit circle, which we calculated to be 2 pi. So there is an equivalence between 360 degrees and 2 pi radians. That's the equivalence. It's sort of like when you convert something like miles to kilometers. They're just different ways of measuring the same thing. And that's what degrees and radians are. 360 versus 2 pi. We usually leave our radians in terms of pi, but if I was to actually work pi into this, that would be about 6.28 radians. So 360 degrees is equivalent to about 6.28 radians. It's a completely different measure with a different unit, but it measures the same thing. So if you think about the whole circle as being 2 pi radians, that means when you're over here at 180 degrees and you've gone halfway around the circle, you've traveled pi radians, because half of 2 pi is just 1 pi. So I like to base everything on knowing the whole circle is 2 pi, half of the circle is a single pi, which means that when you've only gone 90 degrees like this, you've traveled pi over 2, or half of a pi. We usually use RAD for radians in case you haven't picked that up. And what that tells me is that each quadrant here is basically half of a pi. Half a pi plus half a pi plus half a pi plus half a pi gives me the 2 pi full circle, which means down here, 270 degrees, is equivalent to 3 pi over 2, which is basically 3 half pies. So if you think about going a half a pi, another half a pi, and another half a pi, you've gone 3 half pies, and that's a radian measurement. So now you see the basic equivalencies for how degrees convert to radians, and then you can draw coordinate or angles on the coordinate plane in radians instead of in degrees. So I might say, draw me where the angle, switch to a new color here, draw me where the angle pi over 4 radians would be. So it's just like when I asked you to draw me a 60-degree angle or a 120-degree angle on the coordinate plane. Only now I'm giving you the units in radians instead. So pi over 4 radians, think about each quadrant as being a pi over 2, or half a pi. And I'm asking you to draw me a quarter of a pi. That means we're basically somewhere in the middle of the first quadrant because we haven't quite gotten to pi over 2. We're exactly halfway to the pi over 2, or we're halfway to 90 degrees. So a pi over 4 radian angle looks like this, and it's equivalent to a 45-degree angle. Because if pi over 2 is 90, then half of that would be 45. So you're going to start, I know it's an adjustment period, but you're going to start thinking in terms of radian angles as well, and you should be just as comfortable locating those on the coordinate plane as you are degree angles. Now, I know at first it's not going to be that easy, and it's not going to be automatic. So we do want to learn how to convert. In case I give you something like pi over 4 radians, and you can't remember what that means, you want to be able to convert it to degrees so you can put it on the coordinate plane in the right place. So the next slide is going to show conversion. So to convert between degrees and radians, you're going to multiply the degree measurement by the conversion fraction, pi radians over 180 degrees. And as you noticed from the previous slide, pi radians is 180 degrees. So this fraction is basically just saying multiply by 1, but it's going to get rid of the unit you don't want and keep the unit you do want. And then, of course, to go the other way, to multiply the radian measurement that you have by 180 degrees over pi radians, and that will convert to degrees. Let's see how this works. Let's do this example first. Convert 125 degrees to radians. So when I'm given degrees, I want to use the conversion fraction, pi radians over 180 degrees. Notice I'm putting all the units in so I can show you what happens. This degree and this degree will cancel each other out, the unit. which will leave me with only the unit radians, and that's what I want. I want it to convert to radians. And then I simplify what I have left. I have 125. You can think about this as being over 1. So that when you multiply, it's the top times the top, 125 times pi, over the bottom times the bottom, and the only unit left is the radians that we wanted. And then you just have to simplify the fraction that you have left. This simplifies to 25 over 36. There's a pi next to it because we're leaving our radians in terms of pi. And then we just abbreviate our units to RAD. So that's how you'll convert from degrees to radians. More likely, you'll be going the other way. I'll give you something like pi over 12 or negative pi over 12. And you don't know what that is in degrees, but you want to draw it on a coordinate plane. So you're going to convert it to degrees so you can make sure you put it in the right place. So we're going to multiply this one by the fraction 180 degrees over pi radians. And what this lets me do, actually I should have written radians next to this as well, so we can illustrate what's happening with the units. Because the original measurement was given in radians. And I'm trying to get rid of those radians. So by flipping my conversion fraction, now I get to cancel out the unit radians. And I get to cancel out this pi also. So I put the pi on the bottom, so it's going to cancel out with the pi that was on the top. And now I just have, across the top, I just have a negative, and I have 180 degrees. And that's going to give me negative 180 degrees. On the bottom, I just have the 12. And then I just simplify this fraction, it comes out to negative 15 degrees. And so now I would know where to draw that on the coordinate plane. I'd head in the clockwise direction and put my terminal side at 15 degrees. Arc length, so something we've already talked about, this is the last thing in this presentation. Arc length, something we talked about in the previous lesson, is actually even easier to find when the central angle is given to you in radians. So if I give you a circle like this, let's say the radius was 8 inches, and I want us to find the length of this arc AB. So the way that we learned how to do it would be to get the circumference of the whole circle and then multiply by 90 degrees over 360. Instead of thinking about this as 90 degrees, if we do it as radians, pi over 2, then I can use a different formula for arc length, which simply says, do the radius times theta, when theta is the angle measured in radians, the central angle measured in radians. And we get to skip the whole part where we do circumference and multiply by a fraction. We simply plug right into this formula. The length of that arc is going to be the radius, 8 inches, multiplied by the central angle, pi over 2, which gives us 4 pi. And the units on that are the same as the units of the radius, because arc length is just a measurement of length, same as radius is a measurement of length. And so we take that shortcut. It's a lot easier than finding the whole circumference of the circle and then multiplying by a ratio. So it's a shortcut formula that you can use when your central angle is given to you in radians. That is all.